In this lecture, we're going to be starting chapter 24, discussing electric potential. So, experimentally, physicists and engineers discovered that electric force is a conservative force and thus has an associated electric potential energy. The motivation for associating a potential energy with a force is that we can then apply the principle of the conservation of mechanical energy to closed systems involving the force. All right, so we're talking about the potential in an electric field. And if you recall from mechanics, something, let's say if we're talking about gravitational potential energy, you have some reference point. And let's say that that's going to be down here, and that is going to be at maybe a height of 0. Then you have an object held above it, and it's going to be falling down there. But up here, it has some potential energy U that's equal to mgh. Well, we can do the same thing with electrical potential. So if I had a positive charge over here, and it's radiating out its electric field as such, and you're going to have, if there's some positive test charge over here, the tendency of the object is to be going in that direction, right? Because this is positive test charge. There's going to be a force pushing it away. But if you were to push it forward, so basically it's going to have the potential, right, of going away, some potential energy that's just going to increase as the distance increases. But if you try to push it towards it, you're going to end up with some work because you're going against the electrostatic force, and that's going to give you some work. So we'll look into this a little bit later as we start explaining these things. All right, so when an electrostatic force acts between two or more charged particles within a system of particles, we can assign an electric potential energy U to the system. If the system changes its configuration from some initial state I to some different final state F, the electrostatic force does work on the particles. So, like I just mentioned, for instance, if I had two particles, let's just say here and here, and we moved this particle to here, we're going to be doing work on the system. All right, so if the resulting change is a change in potential energy, then our change in potential energy is just the final potential energy minus the initial potential energy, which is equal to the opposite of work. And that's one of the equations that we used in mechanics as well. So as with other conservative forces, the work done by the electrostatic force is path independent, which means if this object was moving from there to there, it can take this path, it can take this path, it can take this path. It doesn't matter. All we care about is the initial state and the final state. All right. So usually the reference configuration of a system of charged particles is taken to be that in which the particles are all infinitely separated from one another. So the corresponding reference potential energy is usually set to be 0. All right. So our UF minus UI is equal to the opposite of work. Well, if we say that our reference is infinitely far away, the potential energy is just going to be 0. All right, so if we say that this is just 0, then really all we're left with is our potential energy is equal to minus the work when our reference is at infinity. Okay, so let's go and do an example. Electrons are continually being knocked out of air molecules in the atmosphere by cosmic ray particles coming in from space. Once released, each electron experiences an electrostatic force F due to the electric field E that's produced by the atmosphere by charged particles already on Earth. Right, so there's an electric field on Earth. These electrons are experiencing electrostatic force due to that field. Near Earth's surface, the electric field has a magnitude of about 150 newtons per coulomb, and it's directed downward. All right, so we're near the Earth's surface. Our electric field is going to be going in the downward direction. What is the change in potential energy, delta U, in the electric potential energy of a released electron when the electrostatic force causes it to move vertically upward through a distance of 520 meters. So we're going against the electric field, which means our force is in this direction, which means we're going to have some work being done. Okay, so the change in potential energy, delta U, in the electric potential energy of the electron is related to the work done by the electron by the electric field. All right, so this is the equation that we had, and that gives us the relationship. So the work done by a constant force F on a particle undergoing a displacement d is given by a work equation. And we've seen that in mechanics as well. We're not changing it at all. The electrostatic force electrostatic force and the electric field are related by the force equation. So this is our force equation, right? And this is just coming from this equation, which is the force over our Q. Where here Q is the charge of an electron in this case. All right, so go ahead, substituting in F for our first equation and taking the dot product, we end up with our work is equal to Q E dot D. All right, and this is just going to be our dot product, so it's just Q E D cosine theta, right? Because E dot D is just going to be E D cosine theta. All right. So theta is the angle between the directions of E and D. Well, notice we have E going down in this direction. We have D going up because that's the direction of motion. All right, so they're going to be 180 degrees away from each other. Substituting all of this in, we get work is equal to negative 1.6 times 10 to the negative 19 coulombs, which is the charge of an electron. Notice how we have a negative sign in there because it's an electron, has a negative charge, times the electric field, which is 150 newtons per coulomb, times the distance, which is 520 meters, cosine of 180. Now, this cosine of 180 is obviously going to get us negative 1, so that'll cancel out with our negative there. So the work is just going to be equal to 1.2 times 10 to the negative 14 joules. Okay, so our work ends up being positive, and our change in potential energy, we know, is the opposite of work. So, so our change in potential energy is just negative 1.2 times 10 to the negative 14 joules. Okay, and that is our result. So we have a negative result. It says that during the 520 meter ascent, the electric potential energy of the electron is decreasing. So as we get closer, as we go against the electric field, as we get closer to some whatever is producing the electric field, we're decreasing the electric field by that much. Okay. So the potential energy per unit charge at a point in an electric field is called the electric potential, or V, or simply just the potential at that point. This is a scalar quantity, so V, which is our electric potential, is equal to our potential energy divided by our charge. So the electric potential difference, V, between any 2 points, I and F, in an electric field is equal to the difference in potential energy per unit charge between those 2 points. So, just going through the math here, we have the change in the change in electric potential is equal to Vf minus Vi, which is equal to our final potential energy divided by the charge minus our initial potential energy divided by charge, or just the change in potential energy divided by Q, which is the charge. Now, if I wanted to relate this to work, our change in potential energy is minus the opposite of work, so you just get minus work over the charge. So the potential difference between 2 points is thus the negative of the work done by the electrostatic force to move a unit charge from one point to another. All right. So if we set our initial potential energy, though, to 0 at infinity, which is our reference point for potential energy, then the electric potential V must also be 0. So we do this because it just simplifies everything for us. Just like when we're talking about gravitational potential energy, you're always setting some 0 point, right? And it's usually at ground level, but it could be really anywhere. It could be 50 feet up from ground level. So it's convenient for us to say that the potential energy is 0 at infinity because it simplifies our equation, so that's what we stick with. All right, so then it's the electric potential V must also be 0. So therefore, the electric potential at any point in an electric field can be defined as our potential is equal to the opposite of work with a reference point at infinity divided by Q. Here, the work at infinity is the work done by an electric field on a charged particle as that particle moves from infinity to point F. All right, so if we're coming from infinity to some final point, that's what the work is going to be. All right, the SI unit for potential is the joule per coulomb. This combination is also called a volt. Right? So we measure our electric potential with a volt, and it's just 1 joule divided by a coulomb. So this unit of volt allows us to adopt a more conventional unit for the electric field, E, which is expressed in newtons per coulomb. All right, so normally we've been writing our electric field in newtons per coulomb, but if we do some rearrangement, we can also write it as 1 volt per meter, and that'll be helpful to us when we're talking about voltage. So we can now define an energy unit that is convenient, one for energy measurements in the atomic and subatomic domain. So when you have things that are really small, 1 electron volt is going to be used, which is just the charge of an electron times a volt. All right, so it's equal to is the energy equal to the work required to move a single elementary charge E, such as that of the electron or the proton, through a potential difference of exactly 1 volt. All right, so the magnitude of this work is the charge times the change in electric potential. All right, and so it's 1 eV. It's just going to be, again, the electron charge times 1 volt. All right, so 1 eV is also equal to this much energy, 1.6 times 10 to the negative 19 joules. If a particle or charge Q is moved from point I to point F in an electric field by applying a force to it, the applied force does the work. So instead of the electric field doing the work, the applied force is going to be doing the work on the charge, while the electric field also does work on it. So the change in kinetic energy of this particle is given by, again, so that in previous or in mechanics, you saw that your change of potential energy is going to be equal to your work. So if you add your work together, the work done by the electric field, the work done by the applied force, you get that the change of potential energy is equal to both of those works added together. So if the particle is stationary before and after the move, right, so it's not moving, then Kf and Ki are both 0, which means that the applied work is going to equal to the opposite of the work due to the electric field. Now, relating the work done by our applied force to the change in potential energy of the particle during the move, one has, all right, so our change of potential energy would then be equal to just the work applied. We can also write the work applied to the electric potential difference, delta V, between the initial and final locations of the particle. All right, so we just take this and relate it to that. And that's just using some of the equations that we had previously. All right. Next thing we want to talk about is equipotential surfaces. And this is what your first lab is going to involve. So adjacent points that have the same electric potential form an equipotential surface, which means that along the surface, your potential stays the same. So this can either be an imaginary surface or a real physical surface. No net work is done on a charged particle by an electric field when the particle moves between 2 points I and F on the same surface. So if I had some surface or a point here, if I move along the equipotential surface to here, no work is going to be required by the electric force or by the electric field. So again, it's saying equal work is done along these paths between the same surfaces. No work is done along the path on the equipotential surface, but if you went from one to the other, you're doing some work. And again, it doesn't matter the path you take, it's going to be the same. If you go from one to the next, let me re-erase this so we can see, this work is going to be the same. So if you go from one surface to the other, no matter the path you take, you're going to end up with the same amount of work. Now, no work is done along this path that returns to the same surface. So if the path took the charge out of the surface and then back into the same equipotential surface, you're going to end up with no net work being done. Here's a couple more examples of equipotential surfaces. So if you had a constant electric field, your equipotential surfaces are just going to be these lines here. So you have these straight lines going up and down. Along those surfaces, no work is required to move the particle. If you had just a point charge, your equipotential surfaces are going to be going out like this. So you have these big rings of equipotential surface. If you had two point charges or a dipole, you would end up with something that looks similar to this. And this is actually exactly what our first lab will look like. We're going to have a positive end and a negative end, and we're going to see what these equipotential surfaces look like in between. Okay. All right, so when we're calculating the potential from a field, let's say we have an electric field. I want to know what the potential is at a certain point on the field. We're going to start with our work equation. So this is just the derivative form of the equation, equal to our force dotted with our distance vector. And we want to change this F so that we are talking about electric field. So we just replace it with Q naught E dotted with ds. The total work is then, so if I take the integral of both sides, I get Q naught, which is a constant, times the integral of E dot ds. And this is from some I to some F position. Oops, sorry. Okay. Now we know that the work is going to be equal to the opposite of our voltage divided by the charge. All right, so we can just rewrite this as our change in electric potential is equal to, the integral of IF E dot ds. Okay, so thus the potential difference, Vf minus Vi, between any 2 points I and F in an electric field is equal to the negative of the line integral from I to F. So this is our line integral from I to F along the electric field. So since the electrostatic force is conservative, all paths yield the same result. So if we set the potential Vi is equal to 0, which is our reference point, right, at infinity, set that equal to 0, then the voltage is just equal to minus integral from I to F of E dot ds. So this is the potential V at any point F in the electric field. Relative to the 0 potential at point I. So if I is at infinity, then this is the potential V at any point relative to 0 potential at infinity. Okay. So let's go to do an example of this. Hopefully some of it will come together once we do that. All right. So in the figure, it shows 2 points I and F in a uniform electric field. So our uniform electric field is going down in this case. We have 2 points, F down here, I up here. The points lie on the same electric field line and are separated by a distance d. All right, so the distance between these 2 points is d. Find the potential difference Vf minus Vi by moving a positive test charge from Q naught to I. So here, test charge Q naught rather, from I to F along the path shown, which is parallel to the field direction. All right, so it's going along the field from I to F, this charge right here. All right, so The distance that is traveled is just ds as we make it smaller and smaller and smaller, so that's what we're going to integrate. We can begin by mentally moving a test charge q0 along that path from the initial point I to the final point F. As we move such a charge along the path, its differential, or displacement ds, always has the same direction. It's always going to be along E. It's following the electric field. Thus, the angle between E and ds is going to be 0, and the dot product is just going to be equal to, so if we have E dot ds, that's just going to equal to E ds cosine theta. Cosine of 0 is going to be 1, so we just have E ds. Now plugging that into our potential difference equation, which is Vf minus Vi, is equal to, minus the integral from I to F, E dot ds, and we just saw that E dot ds is just E ds. So this is going to be equal to minus the integral from I to F of E ds. Now, since the field is going to be uniform, E is going to be constant over the path. So E is uniform, it's not changing. That can be pulled out of the integral. And what we end up with is Vf minus Vi is equal to minus E times the integral from I to F of ds. Well, if we look at this integral, we're taking distance integral from I to F, so from here to here. So this integral is actually just this distance. It's just d. Because that's the distance between those 2 points. So this just simplifies to E d. All right, so our final answer is the potential difference, Vf minus Vi, is just going to equal E times d. All right, that's it for the next lecture. That is it for this lecture. We will pick it up next time.